NASA already has Webb, a telescope built for extraordinarily deep, detailed views. So why is NASA preparing to launch another one called Roman? Because even Webb cannot study something if nobody knows it is there. Think of Webb as an incredible telephoto lens. It locks onto a chosen target and pulls out astonishing detail. Roman will help find the target. Its mirror is the same diameter as Hubble's, but in a single view, Roman's camera will cover roughly 100 times more sky. It is like replacing one window with an entire wall of windows. That does not make Roman 100 times more powerful. Webb will still see deeper. Roman simply looks wider, searching for a rare galaxy, a planet, a flash, or something nobody thought to put on a target list. But the biggest trick is not the panorama. Roman will return to that panorama again and again. A still map of the sky will begin to move. So what can a cosmic time-lapse catch, and why might Webb need it to know where to look? The first things to reveal themselves will be objects that refuse to stay the same. In one frame, there is an ordinary faint dot. In the next, it flares. Then it fades or disappears. One image explains almost nothing. A sequence tells a story. That is how a survey can catch a supernova, a variable star, or a brief event that happened while the telescope was looking in exactly the right direction. How does one camera capture such a wide scene? Behind the mirror sits a mosaic of 18 detectors with a combined 288 million pixels. But this is not a megapixel contest. The whole optical system is designed to collect a huge piece of sky in every pointing. For wide surveys, NASA says Roman could map the sky up to 1,000 times faster than Hubble. Map the sky, specifically. That is not sensitivity, detail, or some universal score for power. That is Roman's real advantage. Not the deepest individual image, but the chance to cover enough sky and return at the right time. Webb can create a spectacular portrait. Roman can identify who deserves an invitation to the cosmic photo studio. If you like explanations without magical claims about being 1,000 times more powerful, subscribe. The difference is about to get even stranger. A planet can reveal itself in two opposite ways. First, it can pass in front of its own star and block a tiny amount of light. The star dims, then returns to normal. If that dip repeats on a schedule, it may be a planetary transit, but a different planet can pass in front of a distant background star. It might even be a rogue world with no star of its own. Its gravity bends the background light and briefly makes that distant star brighter. That is gravitational microlensing. So one planet steals a little light. Another seems to lend the star a magnifying glass. The planet itself may never appear in the image. The change gives it away. NASA's models suggest the microlensing survey could find about 2,500 planets, including free-floating worlds. Separately, the same broad datasets could reveal more than 100,000 transiting planets. Those are two different methods and two different forecasts. They cannot be added into one promise, and a forecast is not a discovery. Planets are only the easiest part of this story to picture. Roman will also try to map things we cannot see at all. Dark matter does not shine into a telescope, but its gravity distorts the light of distant galaxies. Measure enough of those tiny distortions, and scientists can reconstruct where mass is hiding. Dark energy cannot be photographed either. Researchers look for its effects in how cosmic expansion and the distribution of galaxies changed over time. Roman is not an answer machine that will print, "Dark matter is this." It will test models and shrink the room available for error. The mystery may become smaller. There is no promise it will disappear. Now imagine the cost of such a wide view, not in dollars, but in data. NASA expects roughly 1.4 terabytes of raw data every day and about 20 petabytes of processed data over the 5-year primary mission. That is not a folder one scientist copies onto a laptop. More of the work moves into shared cloud systems where researchers can analyze the data close to where it is stored. After processing, the Science Archive is planned to open without a period reserved for only one observing team. An unexpected discovery might come from someone who did not propose the original observation. But an open archive is not an easy archive. Data at this scale still demands computing power, tools, and time. Roman carries one more ambitious experiment. A specialized coronagraph will try to suppress the blinding light of a star and test technologies for observing faint planets and disks beside it. Test is the key word. This is not a guaranteed picture of another Earth, and it is not a life detector. We will only learn the coronagraph's real performance in space. Its greatest achievement may be teaching future telescopes how to see even harder targets. Now return to the original question. Why not give all of this work to Webb? Because Webb's view is too narrow to keep sweeping enormous areas of sky. Roman will search the haystack. Webb can inspect the tip of the needle if the target is compelling enough and a team receives observing time. This is cooperation, not a contest for the title of best telescope. Roman still has to launch. The observatory has been assembled and delivered to Kennedy Space Center. NASA currently targets August 30th at 7:26 in the morning, United States Eastern Time. Whether the rocket, the range, or the spacecraft could still move that date or time. And even a successful launch will not produce a new map of the universe the next morning. Roman must travel toward the Sun-Earth L2 region, deploy, and complete roughly 3 months of checks. Only if that goes to plan can the first survey observations begin. So, launch is not the finale, and it is not the discovery. It is the moment humanity raises a camera designed to be in the right place at the right time more often. Webb asks, "What is this, if we look deeper?" Roman will first ask, "What changed and where?" Which matters more for a new discovery? The telescope that sees deeper, or the telescope that knows where to look? Tell us in the comments.